Let's look at basics of working with fractions so they don't freak us out. Let's look at what information is contained in a fraction. Think of money. You have 3/4, 75 cents. Well, hey, if you chop a dollar up into 4 equal parts, monetarily speaking, they're 25 cents each. Each fourth is 1/4. It's 1/4 of a dollar. So if you had a fourth plus a fourth plus a fourth, you end up with 3/4. So what you need to keep in mind is the denominator tells us how many parts you chop the whole thing into. We're chopping it into 4 parts, 4/4 to a dollar. We have 3, so this tells us how many of the quarters of a dollar we have. So that's how many units it was split up into, and this is how many we have. Well, if you keep that in mind, then 3/4 must be equivalent. This is an equivalent sign. In advanced mathematics, with logic, you start using equivalent signs. So 3/4 must mean that you have 3 times a fourth. You have 3 of the fourth. So those are equivalent. And remember, when you multiply a whole number times a fraction, if you put the whole number over 1 and multiply by the fraction, you multiply straight across, you end up back at 3/4. Simple stuff, but it's important understanding. All right, we can look at unit bars. A unit means 1. So this whole bar would be 1. If we chop it up into 4 equal parts, then we can represent 1/4 by shading in 1 of those 4 equal parts. So we can visualize a fourth plus a fourth plus a fourth ends up giving us 3 of those fourths. All right, now let's think about this. Let's add 3/10 plus 2/10. Let's do it 3 ways. Money, unit bars, and simple arithmetic. So here we go. In terms of money, when you divide a dollar into 10 equal parts, what coin do you get? Diagonally, you get a dime. Okay, so we're doing this in a nice way, because to not use money would be senseless. But anyhow, here we go. We have 3 dimes and we have 2 dimes. So altogether, how many dimes do we have? Oh, well, we have 5 dimes. It's as simple as that. You only add the numerators together. You leave the denominator alone, because the denominator is simply telling you how many equal parts of the whole thing do you have. You have 10 equal parts. All right, now how many of those do you have? You have 3 of those 10 parts and you have 2 of those 10 parts. Altogether you have 5 of those 10 parts. So you have 5 dimes, that's 50 cents. Unit bars can visually picture this for us. You take one thing, but you chop it up into 10 equal parts. Each part is 1/10. How many of the tenths do we have? We have 3 of these tenths. We add to that 2 more of these tenths. So altogether we end up with 5 of the tenths. If we do this arithmetically, we have 3/10 plus 2/10, and we just add straight across and leave the denominator alone. Okay, so those are 3 different ways to do this. Now, let's simplify all of these. Well, a nice thing happens. The most important number in all of mathematics is the number 1. So what we could do, we know that 8 divided by 1, that's a division sign, clearly. 8 divided by 1 is 1. 8 divided by 1 is 8. 20 divided by 1 is 20. Anytime you divide by the number 1, you keep the same value. Anything divided by 1, it doesn't change in its value. Well, let's divide this by the number 1. But the form of the number 1 we're going to use is 5 over 5. That's 5 divided by 5. That's 1. So if we divide this by the number 1, 5 divided by 5 is 1. And 10 divided by 5 is 2. It must be true that 5/10 is equivalent to 1/2, because all we did was divide by 1. And anytime you divide by 1, you keep the same value that you started with. So the number 1 is clearly, easily the most important number in the whole world, and it's also the most important number in working with fractions. Likewise, if we go over here, we're going to just do the same thing. We're going to say, you know what, we're going to divide this by the number 1, and we're going to end up with 1/2. Now, a lot of times you'll see students that are more comfortable with fractions just say, hey, 5 goes into 5 once, and 5 goes into 10 twice, so my answer is 1/2. But what they're really doing, whether they realize it or not, they're dividing by the number 1. 5 goes into 5 once, 5 goes into 10 twice. That's all cross cancellation, as we're going to look at that a little bit more in a sec. All right, now let's do this one. 1/2 plus 3/4. They don't have a common denominator. We haven't chopped the unit up into equal parts, so we can't combine them. We need a common denominator. But first, let's go to money. That's $1/2, and that's 3/4. That's 75 cents, that's 50 cents. Hey, let's make change. Do we all agree that $1/2 is equivalent to 2/4? There's 2/4 in the $1/2. So look at this. If we make change and make $1/2 into 2/4, now we have a common denominator. We're adding 2/4 to 3/4. We get 5/4, which is $1.25. 1 1/4, we have $1.25. If we look at this with unit bars, we can start out with 1/2, but we can chop it up into enough equal parts to match this. So it must be true that 1/2 is equivalent to 2/4. We can now easily combine that with 3 of the fourths and end up with 5/4. 4 of the fourths will give us 1, and another fourth will give us 1 1/4. By the way, in algebra and calculus, a lot of times we're going to give you a break. You can leave your numbers as improper fractions. You don't have to change them to mixed numbers. That's good news. Now here's how we should probably show our work arithmetically. If we're going to add this fraction to this fraction, we need a common denominator. We bust out the most important number in all mathematics. I believe I mentioned it only moments ago. It's the number 1. If we multiply this fraction by the number 1, we're not changing the value of it, we're just changing the way that it looks. So we know that it's worth as much, but it's going to look different. And when you multiply straight across. So this fraction now becomes 2/4. It must be that 2/4 is equivalent to 1/2 because we simply multiplied by 2. So now we can add the 2/4 plus the 3/4. We have 2 of these guys, we have 3 more of these guys. Altogether, we have 5 of these guys. The denominator is nothing crazy. It just tells us how many pieces did you chop the unit up into. The answer, 4 pieces. In the end, we have 1, 2, 3, 4, 5 of those fourths. And that's what's going on with fractions. So we can practice. If we realize that 3 times 1/4 is equivalent to 3/1 times 1/4, then we get the idea that all we have to do is multiply straight across. So if we take 1/2 of 3/10, we can just multiply 1 times 3 and get 3, and multiply the 2 times the 10 and get 20. So our final answer must be 3/20. But here, let's make even more sense out of this. Let's think about money. If you start out with 3/10, a tenth of a dollar is a dime. You have 3 dimes. All right, you guys. If you take half of 3 dimes, isn't that half of 30 cents? So what you should be left with is 15 cents. Half of 30 cents is 15 cents. Now check this out. Our final answer was 3/20. Wait a minute. This 20 means you're chopping the dollar up into 20 equal parts. What coin is 1/20th of a dollar? Well, by golly, it's a nickel. So if you have 3 nickels, that's equivalent to 15 cents. If you take half of 3 dimes, half of 30 cents, you bet your sweet bippy you end up with 15 cents. So fractions make more sense than it might seem at first. Okay, now let's do something a little bit uglier. Let's deal with division of fractions. If you take 1/2 and divide it by 1/4, let's wrap our brain around this first. Here's the deal. Half of a dollar is 50 cents. If you divide that by 1/4, you're asking how many quarters are there in a $1/2. The answer is 2. Just like if you take $10 and divide it by $5, the answer is 2, because how many $5 bills does it take to make a $10 bill? The answer is 2. 10 divided by 5 is 2. 1/2 divided by 1/4 is 2, because it's like 50 cents divided by 2. It chops it up into quarters. Okay, now check this out. We know the answer must be 2. 2 is the correct value to this problem. 1/2 divided by 1/4 is 2, because there's 2 quarters and a $1/2. But we want to go a little further. We want to be more more spontaneous, more act quicker with our fractions than going through the hassle of thinking of it as money or whatever. This is the nerd. He's telling us that we want to change division to multiplication to make things easier, but first, we want to justify this and look at an important idea in number theory. So we're going to take a detour, and here it is. Now, this is pretty cool. The two most important numbers in all the world, for many, many reasons, are 1 and 0. And there's a lot of reasons, but let's look at two of the more important ones. 0 is the additive identity. If you add 0 to any number, you still get that number. If you add 0 to 34, you still get 34. So under the operation of addition, 0 is the identity. It identifies the number that you started with. 11 plus 0, you still get the 11 back. You still identify that 11 is your beginning number. Under the operation of multiplication, the identity is 1. If you multiply any number by 1, you get the number that you started out with. You identify the number that you started with by multiplying by 1. 1 is the multiplicative identity. So 0 and 1, two very important numbers. Now check this out. Think of opposites. Under addition, the operation of addition, 7 and negative 7 are opposites of each other, and negative 3 and 3 are opposites of each other. Under multiplication, 1/2 and 2 are opposites, not 1/2 and negative 1/2. So the question, why are these guys opposites under addition, and why are those guys opposites under multiplication? The answer, what do you get when you add 7 plus negative 7? You get 0, the additive identity. What do you get when you add negative 3 plus 3? You get 0, the additive identity. That's why these numbers are opposites of each other. Now if you go to multiplication, what do you get when you take 1/2 times 2? Well, 1/2 times 2 is going to give you 1, the multiplicative identity. 6 times 1/6 is going to give you 1, the multiplicative identity. That's why under multiplication, 1/2 and 2 are opposites of each other, but under addition, 7 and negative 7 are opposites of each other. Okay, now, with addition, we call the opposites opposites. With multiplication, we call the opposites inverses. Like 1/2 is the inverse of 2 over 1, or the reciprocal. Reciprocal and inverse mean the same thing. So opposites under multiplication are given a special name, we call them inverses. Opposites in addition are the opposites. So why is all that so important? We have a really important math concept that's going on. Check this out. When we have addition or subtraction, if we have a subtraction problem, but it could be made easier by making it an addition problem, look at what we do. We keep the first number the way it was. We're going to change the operation to its opposite operation, which is addition. And we're going to change this number to its opposite number under addition. The opposite of negative 7 is 7. And that is a more mathematically justified reason for why it's okay to change subtraction to addition. We're going to the opposite operation and the opposite number under that operation. 7 and negative 7 are opposites of each other. Okay, now remember, in multiplication, the opposites are called inverses. So here's what we're going to be in the habit of doing. A lot of times in multiplication, we don't want to do division. A lot of times in working with fractions, we don't want to do division. We'd rather change it to multiplication. So we do a similar thing to what we did over here. The first number stays as 1/2. But we are now about to change division to its opposite operation, which is multiplication. If we do that, we're okay to get an equivalent problem if we change the 1/4 to its opposite under multiplication. But its opposite is called its inverse, or its reciprocal. So we flip it. So this becomes like this, and that's the big idea, ladies and gentlemen. If you change subtraction to addition, no problem, man. Simply change this number to its opposite under addition. If you want to change in a fraction problem a division operation to its opposite, which is multiplication, simply change the second number to the opposite of it under multiplication. And we call its opposite the inverse or its reciprocal. And now we can verify that, yep, 1/2 divided by 1/4, we said it was 2. Sure enough, if we multiply straight across, we get 4 over 2, and 4 divided by 2 is 2. So that's the big idea. We hear a lot of times in math, add a line, change a sign, copy, dot, flop. I prefer not to think of mathematics that way. I want us to learn mathematics in a way that makes sense and is mathematically justified, and do less memorization and more understanding. Can you see the similarities between these two things? Changing to the opposite operation is fine as long as you go to the opposites under that operation. That's a mathematical concept that's pretty important. So here we go. Let's just practice real quick. -12 minus 16. If we want to, we have the right to change from subtraction to addition as long as we change 16 to its opposite. What's the opposite of 16? -16. There it is. Equivalent problem. We'll get the same answer of -28. We can change this to addition as long as we change the -4 into a +4. With multiplication, we multiply straight across. 3 times 2, 4 times 3, we get 6 over 12. Life is good. If we have division and we want to change it to multiplication, then all we have to do is say, okay, we can change this. We'll leave the 3/4 alone, change to the opposite operation, which is multiplication, and change to the inverse under multiplication, which is 2 over 1. Multiply straight across, we get 6. Multiply on the bottom, we get 4. We can simplify that later. This guy, let's change this to multiplication. So we have 2/3, change the opposite operation, multiply by its inverse under multiplication. That's what we do there. Finally, cross-canceling. A lot of students are comfortable with cross-canceling. Most kids that come into an Algebra 1 class like, I'm all over cross-canceling, I'm fine. But there's a lot of students that aren't. It's like, I've never understood this. This drives me nuts. I don't understand why students say, look, there's a 2 and a 2. 2 goes into 2 once, 2 goes into 2 once. It's easy. What's the matter with you? You get 5/3. Well, sometimes we need to understand it better so that we can see when and why we're able to cross-cancel. So let's do this. Do you agree that if we took 2/3 times 5/2, remember this is that equivalent sign again, that's equal to one fraction where in the top we're doing 2 times 5, and in the bottom we're doing 3 times 2. Meanwhile, that's equivalent to, hey, remember how 2 times 5 is the same as 5 times 2? Doesn't matter the order we multiply in. So let's switch these guys. Let's make it 5 times 2 over 3 times 2. That's equivalent to putting this back into 2 fractions. 5 over 3 and 2 over 2. Oh, look at that. What's 2 divided by 2? By golly, it's 1. And so we're left with 5/3 times 1. So when students are going up here and cross-canceling, what they're really doing is, there's a couple ways we could think about this. They're really dividing this entire package by the number 1. 2 divided by 2 is 1. 2 divided by 2 is 1. Or you could justify it by saying, you know what, I can switch the 2 and the 5, like we end up with right here. That is equivalent to this, and 2 divided by 2 is 1. So that's how we're able to cancel those guys and be left with just 1, and the final answer is 5/3 times 1, which is 5/3. You want to be able to cross-cancel and do it with understanding, because it makes problems a lot simpler. Case in point, look at this bad boy right here. We could cross-cancel, but first, let's just do it where we said, you know what, there's 4 numbers being multiplied in the numerators and 4 numbers in the denominators. Let's line them up. Let's take this 2 and put it over here. So we'd have 2 over 2. We can't do much with that 3. We'll leave it alone for a sec. We've got this 7. We could put this 7 down here. We have a 5 up here. We'd like to put this 5 over with that 5. Oh, so let's take this 2 and put it under the 3. So in the end, we could rewrite that whole thing just like this. And look what we have. What's 2 divided by 2? It's 1. 7 divided by 7 is 1. 5 divided by 5 is 1. All you're left with the final answer, because you keep multiplying by 1, is this bad boy right here. The final answer would be 3/2. But if we want to impress our friends, we can go in and cross-cancel. So we go in and say, oh, look at that. 2 goes into 2 once, 2 goes into 2 once. I can cancel the 7s. Oh, I can cancel the 5s. And I'm left with 3/2. So you want to be proficient with cross-canceling, and the more you understand about fractions, the easier the fractions become as far as work with them. And then lastly, estimation is beneficial. If you have 3/4, that means you have 75 cents. If you multiply that by 5, you're getting more money than you started with. You get 5 chunks of 75 cents each. But if you multiply this 75 cents, this 3/4, by 1/2, when you multiply by a fraction between 0 and 1, you're going to end up with less money than what you started with. When you multiply these together, you get 3/8, which is less than half. 4/8 would be half, so you're left with less than half of a dollar. So using estimation is good to keep you thinking clearly. When you take a fraction of a fraction, you end up with an even smaller result. There you go, some very important basics to think about and understand in regards to working with fractions.